Hi everyone. I've been working diligently on getting this power supply done so I can get back into the capacitor tester project, and I have one circuit board already designed and installed in the power supply. And there's going to be a video launched on YouTube about this process here very close to the launch of this video here, so keep an eye on YouTube as well. So I figured I would share some of the more intricate details here on Patreon with all of you about linear power supply design and some of the hitches and some of the things that they really don't tell you, some things that are kind of unexpected. Now, I've used the LM723 a lot in designs, and it's a great IC. Now, of course, they've discontinued the dip package and also the surface mount. They have the military version, which is the metal can type, and they're ridiculously expensive. I mean, you know, at least Canadian prices are about $16 each. And of course, the dip works very well. It always has, and same with the surface mount package. But for some reason, they decided to discontinue it, and they're using, or they have still available, a UA723. So basically a direct plug-in, but not a very nice IC. Now, I don't even know why TI is, in this day and age, is even putting something like this out. I don't know. At any rate, I bought a whole bunch of them, and the power supply that I designed has two of them in it. Now, my power supply isn't exactly, designed for absolute, super quiet work, but in the event that I do find some surface mount LM723s or something like that, I will most likely take these UA723s out and put them in. So here's an example of the difference. Now, this is the reference inside the IC. So what we're going to do is we're going to take a look at the reference on this Tektronix oscilloscope. The reason that I'm using this older Type 547 is because most of the modern DSOs and like my digital phosphor oscilloscope, DPO, is noisy. They have noisy front ends, and that's just how they are. And you're going to find that most all modern oscilloscopes have noisy front ends. So even with it bandwidth limited and everything, there's still a lot of noise present. Whereas the same floor on the scope you're looking at right now is a flat line. There's no noise. This is down at 1 millivolt per division, or 1,000 microvolts per division right now. And it's just quiet. As you can see, it's a flat line on the screen, whereas if I show you my TDS7104, it looks like a saw blade. It's just, lots and lots of noise on there. At any rate, so what I'm going to do is I'm going to turn on the the UA723. I'm going to turn that on first. I have the LM on the bench right now. And I'll swap the ICs over, and I'll show you the difference in the reference noise. Now, this is the difference between getting 2 zeros and more. So, like 5.00 is all I'll be able to get stably with a UA723. Whereas if I had an LM723 in there, I'd be able to get 5.000, and then the rest of it would be just a little bit of movement. So you lose a 0 with this noise. So I'm going to turn on the supply. Actually, I'll turn on the... So I'll turn on, I have a little signal tracer I'm using as an audio amplifier, and it's plugged into the vertical output of this scope right now. So we can take a listen to what this sounds like. So I'll shut this off. So that's pure DC. Alright. Capsule discharge here. Alright. So that's just pure DC. When I first turn it on, there's a bit of ripple. This is half-wave rectification on the board. And then I'll just shut it off. So you'll see the ripple, and then I'll shut the AC off, and that's just pure reference noise. That's all that is. That's pure reference noise. Okay, so that's pure reference noise. Now that is with a... Just turn this off here for a moment. Now that is a UA723. Okay, so I'll leave the camera rolling here. I'm just going to swap the IC out on my breadboard right now. I just got to make sure that everything is discharged, because I only have one LM723 left, and I don't want to burn it out. So, yeah, that's good. All right, so I'm just going to pop this IC out. And now I'll install the LM version. So this is made by ST. go. So again, what I'm going to do is I'll turn on the supply, and then I'll shut it off just so it's running on pure DC, so there's no ripple in there. And you'll see the difference between an LM version and the UA, and this is the difference in the reference that they've put inside that IC. It's really quite disgusting. All right, so here we go. All right, I'll turn the speaker on, and I'll shut the supply off. That's the noise in an LM version. That's it. All right, I'll do it again. Pure DC. I don't even know if you can hear that coming out of my audio amplifier, which little curve tracer or signal tracer. It's just about quiet. So why they've discontinued it, I'll turn the audio up on, I'll hit it one more time here. I'll turn the audio up on the signal tracer here just so you can listen to it. I'm not sure if you can hear that in the mic. So here we go. I'll turn it up. So that's it. That was my signal tracer almost cranked right to the top in the high gain on position. So that'll give you an idea of what's going on here. So the UA723 by no means is a replacement for the LM723. So if you're going to put it in a power supply where you're only going to look for a few zeros, it's absolutely fine. And in the power supply, this Anatech that I just worked on, that I designed a new board for, I really don't need anything more than that at any rate. I don't need anything more, but if you wanted to make a nice, very accurate, quiet supply, the LM version is what you want to look for, or just don't either, design something completely different with a separate reference and, using op amps or something like that instead. At any rate, so there's an example of that. So what I'm going to do is I'll move the camera now, and I'll give you an example of the differences just looking at a voltmeter, and I'll show you the schematic, and we'll take a peek at the circuit board here, and I still have one more to do. So since I have one board designed, which is fresh, so it's no revisions, it worked out perfectly with the first go, but I have one more board to do. But now that I have all the measurements and everything taken down, the board, putting the whole thing together and aligning it and putting it in the power supply should, be a half a day or something like that, and then the whole power supply will be up and running again, and it should be good for use. So anyways, I'll move the camera here, and I'll give you an example looking at a meter instead of just listening to noise, and you can see the difference between the two ICs. Let's take a look at the difference between a UA723 and an LM723 using the meter. So this is the output of the power supply here. So this is basically the power supply on the breadboard using the pass transistors in the power supply. So this is the output here. We don't really need to pay attention to that. We want to take a look at the negative 5 volt supply because that's what I'm focused on right now, and that's what I'm looking at. That's where we're listening to the noise from the reference. Now, in either supply, if I was to listen to the reference, it'll make the same amount of noise. I can take any number of ICs I have and pop them in, and I get all the same results, surface mount or through-hole version of the UA723. All right, so I'll turn this on. So this is the 5 volt supply right here. I don't have it set to exactly 5 volts. And this is just the output, some random value. So I'm moving things on and off the breadboard so much that I haven't even bothered trying to set it to 5 volts. So as you can see, we're going to get 2 places. And then after that, it's just going to be noise. Now, that's just noise. You even click on the filter here. And you can see, nothing's going to help, right? So I can do whatever I want. I can play with the reference section, and I can work on it, try to add filtering, do whatever on the outside, and it'll just stay like that. And I experimented with a whole bunch of these ICs to see if I could get it quiet. But, in the IC itself, there is a bunch of push behind that, so there's some current being supplied, and you can't get rid of the noise. You try to get rid of the noise, and bad things happen to the IC. So there's quite a few sacrificial ICs that that went in the trash can because I was just spending a lot of time trying to see if I could just lower the noise somehow without, a really elaborate circuit on the outside, right? You shouldn't need to do that. You should absolutely not. So this is what you're going to deal with. Now, the IC will start up like this, and it'll be like this for a while, and sometimes you'll find that they'll climb up to a certain voltage and then they just get really noisy, and others will just start like this. So there is some variability in the UA723 I found through all of the ones that I've bought. And I bought a whole bunch of them just to do experimentation with, to compare them to the LM723. Okay, so that's what we're looking at. This is what we're going to be seeing with a UA723. So I'll shut off the supply, right? Of course, this is pure DC right now. Again, makes no difference, right? Because we're looking at the reference here. All right, so I'll just let everything settle off. You can see the power supply is turned off right now, so I'll let the caps discharge because I don't want to damage my LM version. And we'll take a closer look at the ICs here in just a moment. I'll move the camera around and I'll show you the actual ICs that I'm using, and we'll take a look at the power supply, and I'll show you the design as well. I didn't release the schematic on the YouTube, in the YouTube video at all, so I'll show you the schematic of the remade power supply here. It works very well. I'm quite happy with it. The IC, of course, no, but the power supply itself worked out very, very well. And I'll explain some of the intricacies of linear power supply design. And stuff like this right here that you're looking for. This is stuff you don't see. They don't show this stuff. You know, this is the kind of stuff that just isn't publicized. You don't see this information anywhere. Okay, so I'm going to remove this IC. Just take it out of the breadboard carefully. That is the UA version. I have lots of them. I'm not too concerned if I damage one of those. But this one I am concerned about. Alright, so move that up. Nothing is touching. Breadboard is good. Okay, so now, here we go. Turn this on. And of course it will stabilize. It'll warm up and it gets very stable. Look at that. We gained a digit. Look at that. It's just very slight flicker over here. So we gained one solid digit, and it's just going to flicker over here. And that's right at startup. That's not even warmed up or anything. When it warms up, it gets better. So now when you look at the UA version compared to the LM version, you know, it's really quite ridiculous, the difference in the two ICs. And, you know, what would it cost TI, really? You know, to put a proper reference inside the UA723 instead of that, right? So I don't know whether they've done this. Maybe they just want to sell the CAN version, the expensive CAN version now or something like that. I really don't know. So, as I say, you know, it'll wander a little while until it gets warm, and then it really gets nice and stable. And this is an ST version right here, right? So I'll shut this off. So it's just pure DC too. Right. And it's just going to discharge now. So we gain an extra digit there. And even the far digit is stable. That's the difference in the noise. And that's just the reference. That's all it is inside there. So if you were to design a power supply, if I was going to design a nice quiet linear power supply, it would have a separate reference, a reference that I could actually even make more silent, you know, so external from an IC, because this reference is embedded in the IC, so you can't do really anything to make it any quieter, right? At any rate, so that's the difference between the two. So I'll move the camera over here. Oh, I'm going to show you this too while I'm here. If you recall the flat line on the Tektronix oscilloscope, that's what you get on a modern DPO or DSO. And that's bandwidth limited right there. See if I can get the focus on the screen. Move this over just a hair. That's what I'm dealing with. That's the noise that you deal with. So if I was to take the signal out and plug that into my audio amp, we'd be listening to that on top of the noise, right? So that it'd skew the results. Whereas on the old Tektronix Type 547 with the 53D/54D plug-in, it's silent, like dead silent. If I put a cap on the end of the BNC jack on the front, it's no noise, nothing. Properly designed oscilloscope. The old Tektronix 547s and all of the 500 series scopes, it's just, they're properly designed. So obviously, you know, this oscilloscope here, back in the day when it was brand spanking new, was a fair chunk of change. And, you know, you would think that they would, you know, get the noise floor on the scope at least to a silent level for the price of the scope back then. But you find that all of the newer DSOs are like this, right? Of course, these scopes themselves are loaded with switch mode power supplies and, you know, lots of digital stuff roaming around inside there, so it's bound to have a bit of noise. Whereas the old Type 547, you know, they're designed for this kind of work. They're designed for analog work, designed to, you know, no switching supplies inside. It's there, you know, everything is linear and it's just quiet stuff. At any rate, so there's an example of the two scopes, the differences between them. This again is just sitting here. Now, if I cap I'll back this out here. If I cap the input, right, cap the input down here, it doesn't make a difference at all. Like, I mean, I'll give you an example here. I'll put a termination on the input, just to be fair. There we go. No difference at all. It's just internal noise in the scope. So, at any rate, I'll move the camera and we'll take a look at the design, and I'll show you the schematic and talk a little bit more about linear power supply design. Here's one of the new power supply boards installed in the power supply. So this one here is the old one. Again, this can all be seen in the YouTube video. That'll be up right around the same time as this one right here. So I only have one of these built at this time. This one here, when I build a board, I only want to print one off just in case there are some, you know, hidden hitches in the board. But this one here worked out flawlessly, so I just have to make another one for the other side now. But this is the board, and, you know, what's remaining, I've used a few components off of this board. Again, all explained in that video. If I was to pull this out of here and then, you know, show this to you here and put it all back in, it's just, you know, more time. I want to get this supply done so I can get back into the new piece of test gear that I'm designing here, that new capacitor tester. I want to get right back into that. So I don't want to delay this any further than I already have been delayed. So this is all stuff here that was not shown on YouTube. So this here is the layout. So this is me looking through the top side of the board. So this is the bottom side, right? That's the top side there that you can see. There's not a whole lot going on the top side. I've used a bunch of copper, you know, to sink off some heat from the diode, and I installed a little sink. I'll zoom in on that here in a moment. Put a little sink on the top of the diode and things like that. So, and I'll talk about the schematic here and explain what's going on here in just a moment. So this is the component layout map. This is how I print things out for myself, so I don't bother, you know, sitting in there and editing everything in all really nice like I do when I, you know, expose things here, or, you know, release a design here. I use my own scribbles, and this will go into a file for myself. So at any rate, so this is the looking at through the top side, but when you're populating the bottom side, the board is flipped over. So this is the side that I use to populate the bottom. So because when I'm designing this, I design on the computer, I'm designing it looking like this. So as I'm designing it, I'm knowing where all the places are. I'm actually designing backwards, okay, because the ICs are on the other side of the board, and I'm looking at the bottom side of the IC. So I design backwards on the computer as I'm laying this out. And then when I go to populate the board, I'm looking at it, you know, flipped over, right? I'm looking at the mirrored image of it. So in order to make things easier on myself, what I do is I print this off, and I just take the values that I've designed when it was designed basically backwards and put them on this. So when I'm looking at the bottom and I'm populating it, it's just, I don't have to think about anything, right? So that's again, this is just flipped over, right? So if you're to, what you just looked at was like this. So this is just flipped over. And that's the layout. So I'm still using the pass transistors and the actual driver, Darlington driver in there. And here's another little piece of information about linear supplies that you just don't hear about. This stuff isn't talked about at all. So I will talk about that so you guys know about this stuff. So here's a schematic. I'll put this down so I'm not shaking as I'm holding this thing, because I haven't had my daily intake of coffee yet. It is 2 a.m. in the morning. This is when the best things happen. 2 a.m. in the morning. That's when best things get designed. All right, that's about as good as it's going to be. Pardon my scribbles. This is what I use for myself as I'm drawing this out. Yeah, it looks like a bunch of, I don't know, looks like a rat's nest. But anyways, it's this is what I use to design it. So this is the output section that is in the actual supply. So that's in the supply. Those are the transistors that are on top of that black heatsink. Now, I've only drawn this as a single transistor, but it's actually a Darlington transistor here. Now, this is a 25 volt power supply, and this here is the 2N3055, and this is actually what's driving the output binding post, right? So this is where the, your output is on the front of the unit. Well, you'll notice that under no load, the collector voltage of the 2N3055 is only 21.7 volts. All right, so this is a 25 volt supply, right? And, it'll be 27 volts, whatever, with the VR turned right up, and that of course is set by this right here. If I change this value around, I can make it go all the way up to about 30 some odd volts, right? But at any rate, so this is 21.7 volts, but yet it's a 25 volt power supply. Now you'll notice that they have full wave rectification on the transformer here. That's the green windings here. They have full wave rectification, and what they're doing is they're feeding that into the driver, Darlington driver. So it's 44 volts on the collector of the driver, yet you'll see here the center tap. They've taken the center tap of the transformer and they've rectified that, and it's also filtered here. I haven't drawn in the filter, but there's a filter on that as well, and that runs over here up to the 21.7. This is the 21.7 volt into the collector of the 2N3055, and that's driving the output. Well, you're probably thinking to yourself, well, how are they getting 25 volts out of the the section here right at the binding post out of the emitter when it's only 21.7 volts. What they're doing is they're actually taking some of the current from the Darlington and feeding it through the base and out the emitter. So this is actually doing some of the driving as well, the Darlington behind it. And the reason that they're doing this, you might want to pause the video and guess why they're actually doing this. If you want to guess before I explain this, you pause the video now, think about it, and then start the video back up again. Okay, so the reason that they're doing this is because there isn't a lot of drop across this device. They want to keep the drop across this main device down as low as possible. Less drop across the device equals less heat, and that's how they're getting 2 amps continuous out of one 2N3055 transistor without it burning up. If I was to take 44 volts and run that directly to the collector of this 2N3055, which is absolutely possible. I could do that. But if I was to load this to 2 amps, that transistor will burn up. It'll just, even on a heatsink. Want to know how I know this? So at any rate, they'll burn right up. Absolutely burn right out, because there's so much drop across the device. The more drop you have across the device when you're drawing current, it just turns into heat, right? So by keeping the drop across the device low, right, and then using the Darlington to actually feed some current, if you look up the specs for a 2N3055, you can see how much base current it can deal with. It can deal with a lot of base current. What they're doing is they're just sharing, and it works very well. It's another very interesting design, and this was designed by Anatech. So it was you'll see this in some laboratory power supplies, but for most of the time, if you're looking at like an Astron or a Trip Light, or if you're looking at the standard kind of power supplies that you'll see, in the ham radio world or CB world, or just, battery charging world, whatever, you won't see this. They don't do this kind of stuff. This is pretty elaborate. So this is all left the same. And when I redesigned the new board, which is right here, I designed it to be a direct replacement. So all the wiring just fits onto the same terminal. So what I've done is I've removed all these little connections. These are just unplugged, right? And you pull off little connections here. I've removed them all from here and put them into this board here. And that was quite a job, because they've actually crimped them on the bottom side. Knobs mushroomed them on the bottom side. So I had to desolder them and then take that crimp and put that, basically pinch it together here. And a light that's starting to flicker on the side here. I don't know if you can see that. It's starting to drive me nuts. One of these IKEA lights. They all do that. All of these IKEA lights, you buy these IKEA lights, they're great, they're flexible. These things here, I use them all the time for everything. And you get very short period of life out of them, and they start to, you can see I can move them all over the place, and they start to flicker. Anyways, obviously they're running the LEDs pretty hard. I notice that they don't carry these things anymore. I don't know how many of these things I've gone through. Just keep throwing them out. At any rate, so back to this. So they mushroomed the connections on the bottom side here. So I had to desolder them and then pinch this together and then pull them out of the top side on every single one of them. And then on the new board, what I did is I soldered them in on the top side and on the bottom. So there's a pad on the top where they're soldered and a pad on the bottom, so they're very solid. So this new power supply board is serviceable. I can very easily service this, even though it has surface mount parts on the bottom of it. Changing one of those ICs is 5 minutes or something like that, right? So again, if I do find some LM, surface mount LM versions, I'll probably just pull them off and put them on there. So just give me that extra digit, just because, again, it's well filtered. Anything past 5.00 volts or, with 26.00 volts or whatever I have it set at is not too big of a deal. But if I go down and, I'm down to a volt or something, it's 1.000 volts, that last digit will flicker. And if I want to go down to the millivolts, which this will do, it'll start to flicker too. So here's a look at the actual board as I had to map it out, right? So I had to measure the distance between all the, the mounting holes and the cap. I tested these caps. These caps are usually always very good, and these caps are still very, very good. Nice big thorough test on these capacitors. No problems whatsoever. So I like to use these just because they keep the look of the supply. And they're right at their value, low ESR, everything. It just works fine. So I figure I'll use them. And if for some reason they fail, I'll just replace them. Not a big deal. Anyway, so this is the layout here and what everything does and where everything ties in. See, there's a pass elements. This is the Darlington driving the 3055. And we have this here, the current sense and output leads and all this kind of stuff. We have all of this on here. So this is all my measurements, is what I use to design this new board with new caps. So because the LM 723 and the UA 723 does not go down to 0 volts, in order to get it to go down to 0 volts, I need to design a negative voltage regulator. Now you're probably saying to yourself, why not just use see, I have a negative 5 volt supply here. And then that negative 5 volt supply allows me to lower the floor here so that I can bring this IC here, which replaces the MC 1466L that I removed out of this thing. So I can bring this down to 0 volts. And there's a zero adjust and all that on the bottom here that I explained in the other video as well. At any rate, you might be asking yourself, well, why did you design a 5 volt supply when you could just put in like LM7905 in there? Your result is only as accurate as the weakest point. So if this is flickering around at 5.01 and it's going 02, 03, 04, it drifts or whatever, that's drift is going to get carried over into this. So I'm going to see movement on this side. So the best thing to do is to create a negative 5 volt supply with the same IC. And the ICs will hold very well. Like, if I set this to negative 5.00 volts, right? If I set it there, it'll stay there, 5.00 volts. It doesn't move. It might go to 01 when it gets very, very warm. I'm not worried about that. So now, if I have the LM723 in here instead of the UA, I would get that extra digit. It'd be even a little bit better. But this just sets the floor. That's all this does, is sets the floor, the 0. And then once I set that all down, so this is the pass element here, and then of course this goes to the actual negative. So we have the negative 25 volt supply coming in here from the filtered rectification, there's half wave rectification down here off of the red wires, right? And then that runs up to here, and then on the emitter, because it's PNP pass element, what this does is this runs over to the negative of the IC, right? So the negative of both ICs is tied to this, and then that allows me to use this side here to lower the floor, basically. So I'm using this to null that offset off on this one side with pin 5 and the reference here. And then on the other side, I use this as a voltage adjust. So this right here is the sense, right? We have the adjustment here in the sense, and this always has to be tied to the binding post. So whenever you're designing a power supply, you wouldn't want to tie this anywhere in the supply. This has to be, the sense lead always has to go right to the post, because you're going to get dropped through the rest of the system. I wouldn't want to tie it over here, because we would, we'd get dropped through everything, right? So we want to sense that. So whenever you're dealing with the sense leads on any type of an IC, it always has to go to the binding post. Technically, even the grounds should. So all of the ground, the whole grounding system, whenever you see a ground here and everything, they should all go to the binding post. And then from the binding post, it should run back to the actual filtered supply. In this, it's not possible the way that they've built this, because it's so tight. I can't really do that. So I've got a really thick negative trace that runs up, and then there's a really thick black wire that's just got a short jump to the ground post on the front here. So that's something that's very important in linear supply design. If you were to say you didn't need to have it go to 0 volts, if I just wanted this to end up at 2 volts, the UA 723 and the LM 723 most of the time will go down to about 2 2.5 volts, something like that. And that's the floor for it, right? So if you were to design a power supply like that and you didn't have all of, this stuff over here in there, so it just goes down to 2 volts, you would want to, again, tie everything, all the power supply grounds and everything would all join at that negative post. So kind of like a star grounding system, and then it would run from there back to the supply. And then when you draw current, if you draw current from the posts and you have your voltmeter across it, you're going to see almost no movement. All right, so if you had, say, a really high current supply, like a 30 amp supply, and you have the binding post running over to a ground, that wire that runs from the binding post to the ground is a resistor. So you're going to get drop across that. So again, you want everything as close to the binding post. That's very important in any type of power supply. And you'll see that even in my little boost supply. When I designed that boost supply, the 29.5 volt boost supply for the capacitor tester, you'll notice that how all the grounds are attached. It's very important in the design. All the grounds that are attached on the bottom of this thing too, if you take a look here, all the grounds, they all run up to a central point, right? Everything is just right to this one point, to this ground. And then on the top side of the board, there's a really thick trace. So when I tighten the capacitor down, it connects the bottom side of the board to the top side, and then that runs over to this negative terminal here. So it's a big thick trace that runs over here like so. And then that just makes a short jump over to the binding post here. Very, very important. Star grounding. You can't just tie grounds in anywhere. So you have say you have a ground here and I wanted to tie a ground over to here. And then, say instead of having this ground here from this supply, right, running up over to this ground here, say I wanted to attach that over here, right? Well, we're going to see drop. Right? You see drop in all of these traces. So what you want to do is you want the central grounding point to here. Now, if I wanted to minimize the drop in this supply even more, so there's a little bit of drop. So say it's sitting at 5.00 volts. If I load it, it'll go to 4.99. Okay, so whoopee-doo, right? Yeah, there's basically nothing there. But if I wanted it to stick exactly at 5 volts, again, this technically would be the binding post. Everything would join at the binding post, and then the grounds would all run back. So the ground to the UA723 and everything would all just tie right to that post. Very important design. With this, if I wanted to minimize it, I could put a little tab on the bottom of the circuit board and run a really thick wire also right up to that ground post to minimize the losses that are in the trace and everything. And I might get that rate to stay at 5. But I'm not really too worried about that. Again, it's a 2 amp supply, right? I'm not using this for any super finicky work. This is designed for, as long as it's quiet enough for, what I'm doing when I'm designing the testers and all the little pieces of equipment. If I need anything that's more quiet than this, I'll run leads out of this and I'll run external filtering on a separate board and then back out. I can do that as well, right? There's lots of ways around that. It's unfortunate, as I mentioned, that the noise is originating right in the source. And of course, there's push behind it as well through the IC, right? So there's delivered current and stuff. So it's hard to get rid of that noise through all of the internal circuitry. So do I have a picture of the internal circuitry here of that IC? I did. I also have the 1466 here as well somewhere. But anyways, I got so much paperwork and everything scattered all over the place just because there's so many things going on at once here. I need to, I'm working as hard as I can to get back into that tester, into that piece of test equipment. And yeah, it's just one thing after another. At any rate, so that's what's going on here. What else can I tell you about this design? I can zoom into this here a little bit and show you what's going on, more of the aspects here. What else should I tell you about the schematic here? More hints and tricks that they don't tell you. Oh, here's another thing that any experienced power supply designer would go, what are you doing here? Okay, so here it is. You'll see a 3.3K resistor here. This is in the data sheet. That's tied directly to the base, but there's also a 3.3K resistor in line from the drive. This inside this IC is a Zener diode, and they use this Zener diode in the negative configuration to run out. Normally, pin 10 is what you drive pass elements with, NPN pass elements. So there's a Zener diode that runs off to pin 9, and for the negative side, you use that pin at any rate. So why do I have a resistor in the base of this PNP pass element, which is this little teeny transistor here? Why do I have that? Again, you might want to pause the video and guess. Do that now, and I'll explain exactly why. Okay, so the reason that this resistor is here these ICs, and the LM version or the UA723, if you look at them the wrong way, they burn out. All right? If you go and make a coffee, they burn out. If you go and walk your dog, they burn out. If you go shopping, they burn out. These ICs are some of the most tender ICs that I've worked with. You know, you think CMOS stuff is tender. I don't know what the deal is with these things. These ICs are very, very, very touchy. You make one mistake. If I want to say I'm running this pass element here and say I add a capacitor. All right, so onto the negative 5 volt line, say I'll add a 50 microfarad capacitor just so that, you know, I add a little bit more filtering, plug it in, that IC's dead. Like that, it's dead. Just that easy. So I want to say I'll move that capacitor out and it still has a bit of a charge on it. Okay, maybe drained off a bit, plug it back in, boom, that IC's dead. That's it. The IC's toast. That's how quickly these things go. So this is added protection. So what this does, this resistor here in line with the base here limits the amount of current that if something is drawn heavy on this side, what's going to happen is the IC furnishes enough drive to make the pass element work properly under this amount of load and in this supply. How do I know this? Because there's a lot of time spent in this little circuit here looking at different resistance values and making sure that I can protect this one IC if this one goes away. So this IC here, if anything goes wrong on the output section here, and I've added a lot of protection, you can have a Schottky diode across the output and things like that. So the reason that I'm using a Schottky is because the forward on a Schottky is, you know, around 0.3, 0.4, whatever you have, you know, whatever type of Schottky you're using, you have a low forward on it. The forward of the Schottky is lower than the standard junction or whatever inside these ICs, right? Because these are just made with, you know, standard transistors inside these ICs, right? So what turns on a standard transistor? 0.6 of a volt, right? Well, if this is going to clamp at 0.3, I have that extra bit of protection, right? So that's why if you ever want to put a protection diode in something, use the protection diode with the lowest forward you can find. So if anything is ever reversed, you know, if something is reversed, you know, it's going to clamp at, say, 0.15 or 0.2 or 0.3 of a volt. It'll clamp it before it gets up to that, you know, 0.6 where other things can start to get damaged. There's another little trick. So if you have any ham radio equipment, a lot of the times they just put a standard diode across the line. So if there's any reversal of the line, that diode is designed to clamp and short. Well, if you get a diode that clamps earlier and quicker, you're just going to have all that much more protection. Something to keep in mind, another little trick there. At any rate, so back to this. So what ends up happening here is that, so if something goes wrong in this section, this IC burns out, there's a chance that what it's going to do is try and feed a lot of, you know, voltage. If something goes wrong in here, it's going to try and feed it back into this negative line here again. So if something like that does happen, we might deal with a hot pass element here or something like that, but chances are we're going to save the IC because this is going to limit the current. Okay, so the IC furnishes enough current to drive the negative 5 volts, and if you change or vary the load on this side, there's almost no change on this side whatsoever. Almost no change whatsoever, yet there's that added protection that if there's any type of a surge or if you drag this down really fast or something like that, it's not going to hurt this IC, and that's the only reason there's this light value of current limiting resistor there. Now, all of you that know about transistors is they are current-driven devices, so they require current to drive them, to turn them on, right? So whereas a FET, they're like a vacuum tube, right? They rely on voltage. They take basically no current to turn them on or off. Transistors are different, right? Bipolar device. That's the way that they work, right? PNP and NPN, you know, that's the nature of the beast with transistors. So since these things take current, right, and you know, this is a pass element, I just want to protect that IC, and that's why that's there. Another thing that you won't see in design like this a whole lot, right, because most of the manufacturers, they'll skimp on that, right, because they don't care if this thing burns out, well, what's the difference of changing this one as well? Well, when I design something on my own board, and if something goes wrong, say I do something wrong, or it magically fails like this thing, I don't know why this power supply failed. And I have absolutely no idea. I shut the thing off, turned it on, it didn't work. That's it. And both sides too. So this side and this side. So I'm thinking maybe I hit the case of this thing with, you know, really high static, or maybe, I don't know, maybe there's some really bad voltage excursion or something in here. I really don't know. If I knew, I would say it. If I zapped this thing, I would openly admit it. If I accidentally fed 1,000 volts into this thing, I would tell you. I don't know why. If I made some grand mistake, you would know about it. So, no clue. At any rate, so that's why I designed this. So this should be pretty resilient. There's lots of protection in here. There's a cap across the output, you know, resistor, Zener diode, not Zener, what am I saying? Schottky diode here. And yeah, there's lots of protection there. And there's even more on the actual, I've added more of these than on here than there's actually on the schematic. There's one that protects the sense terminal here. And no, this is the out. Sorry, this is the sense post here. This is protecting the sense. This is the out over here. So I've added a few more of them here. I'm looking at this in a monitor, pointing at, trying to aim at things. And yeah, so there it is. So there are the ins and outs of this power supply. I'll zoom into this and quickly show you this. All the details and everything will be in that YouTube video. So at this point, I would just be repeating myself. So I'll just move this out of the way. Everything is discharged. There's about a gazillion wires on this thing. When I'm doing my experimentation, I actually put double-sided tape with the VRs on the front side of the panel so I can turn them and they just stay there so nothing moves. All these little tricks of designing. Because here's the, oh, by the way, here's the IC. See, these are the UA versions. UA723CN is that, there it is. And I also have the surface mount versions. Right? So here, so let me grab one of those. I'll show you those. Sorry, bump the stand there. If you could only see behind the camera. So, all right, put that down here. And here is the surface mount version right there. So that's what's in this supply here. So they work well, it's just that they're extremely noisy, and I have no idea why TI has done this, and maybe I'll send TI a message. What I'll do is I'll make a noise generator out of one of these ICs. A little audio amp on it and make a noise generator. The UA, we'll call it the UA723 noise source. Instead of reference, whatever, we'll call it a noise source or something like that. That probably get their attention. So I don't know why they've done this. Again, you know, I'm just going to disconnect all this stuff over here. Move this out of the way. So I don't need to demonstrate that. I got this board already done. I'll make the second one. Get that out of the way. Okay, zoom on in. So that is the top side of the board right there. I've explained this little diode here with the heatsink that I've added. That's all explained in the the other video as well. So the filter, and this drains off this capacitor here. So these here and this here holds up the negative supply and keeps everything stable as everything drops off on the main supply. So this has to drop out first. If not, you get a voltage spike as it's dropping off. So the voltage will you know, come down, right? When you shut the power supply off, it'll get to a point and it'll start to climb back up again. So that could be dangerous if anything, you know, so say you're sitting at 1 volt and you shut the thing off and it goes down and then it'll go way up, maybe up to 3 or 4 volts. So what this does is this drains this off first. And the reason that these capacitors are so big, again, as explained in the other video, is it holds the other supply up so that it doesn't do that. So it just drops off and then raises just a hair and then completely you know, falls off. So there is no raise there, like it won't do that. So that's the reason that these filter cans are so big on the half-wave rectification over here. Things like that, you know, lots of things in the design plan, as I explained there. I can get really, you know, deep into the whole thing here. As you can see, as I soldered the top side of these connections here, so let's see if I can pull one of these off. They're on there pretty good. There it is. So that's what they look like, right? These little pins that I've soldered on here. I removed these out of the other board, and then, you know, these just fit on like so. Like so. And it's a direct replacement, just snaps in, and I just put all the wires onto the same place. And I, changed this VR. That 10-turn VR is driving me nuts. Put a single turn in here, and that made things quite nice. Bottom side here, that is a quick view of the bottom side of the board here. Again, this is all seen in the other video. So bottom side right there. And that's it. So it's just about done. So I'm going to dive into, linear power supply design a lot more. As I say, I'm designing that capacitor tester right now, and me going into, designing linear power supplies and going right off the path here and starting to talk about this is, really not right. I want to get that piece of test gear design, and then I'll dive into linear power supply design a little more. And of course, I've designed a bunch of boost supplies and explained stuff about switch mode power supplies in the past, and I'll dive into that more as well here on Patreon. So we'll design some supplies together. We'll design some supplies for older radios, to make B+ for older radios, and we'll design large variable power supplies like this, maybe 10, 12 amps, something like that. If you have any type of a radio, car radio, CB radio, if you want to charge batteries or whatever, we'll design some power supplies with a bunch of pass elements and things like that. I'll go through all the steps and all of the thought processes and designing that as well. This one here worked out very well. There's no revisions. It's just the way it just turned out. I put the whole thing together, worked flawlessly. I was very happy with that. So now that this is done, I have another board to do. I have to make the other board and get that out of the way so that I can get right back into the design of the new tester again. All right, I hope you've enjoyed this and some of the little secrets that aren't talked about in linear power supply design. And when I say they're secrets, I'm not kidding. They don't talk about this stuff, like the pass elements. Try and find information on that anywhere. When they talk about, this 44 here and the 21 here, or when they're talking about reference noise and any examples out there, try and find some examples of it. It's just not existent. I don't know why it isn't. So I guess there's maybe not enough people, or maybe people think this is some sort of a trade secret and they just want to hold this stuff secret. I really don't know, but this information isn't out there. So as I come across more of this stuff, I'll share all of this information with all of you. So if I find a solution to making references quiet, or if I make a very quiet reference source, I'll share that with you as well. So that's what this is about, right? So let's enjoy this and build stuff together and, learn things together and have some fun. All right. I hope you enjoyed. Talk to all of you very soon. Bye for now.